Okay, Namaskar. Very pleasant afternoon, just after the lunch break. And it's another brilliant session which is in the offing, which is in the beginning. This is day two. This is day two.
Screen.
Yeah, this is day two of Bharata-Tirtha, international webinar on Indian knowledge system as organized by IIT Kharagpur. And this is technical session 3 on numeral systems.
Joy, the audio is not coming up.
You're not listening to me? You're not hearing me?
I'm able to hear you.
Audio is not coming up.
Audio
properly.
is not coming up.
May
I
ask
can
others
hear you.
to confirm?
Yeah.
Yes, I can hear Professor Joyson.
Okay. Okay. What about Ramji? Ramji, you can hear me?
I'm able to hear you.
Okay, fine. What about Professor Khare? Professor Khare, you're able to hear me?
Clemency, I can't see Clemency.
You are able to
Broken.
hear
It's completely broken. I'm not able to hear anything.
Yeah. The network is fine. It's showing fine here. Yeah.
I'm able to hear you perfectly.
Yes. Yeah,
Okay.
it's fine now. It's fine now.
Oh, okay, fine.
Yes,
fine.
I'm able to hear you.
Okay.
Please go ahead. Please go
Okay,
ahead.
so let me start again. Welcome to Bharata-Tirtha. This is day 2, afternoon session. We expect another brilliant session on the numeral systems, Vijayanita and Jyamiti, and all the domains under the Vedic and ancient Indian mathematics and its relevance in the contemporary world. So it's my pleasant duty to give the floor to one of our esteemed professors of planning and coordination, Dean of Planning and Coordination, Professor G.P. Rajashekar, who is going to chair this session, and he will be supported by 2 reporters, Professor Jitendra Kumar and Dr. Swananda Khare, as one from IIT Kharagpur and one from beyond the domains of IIT Kharagpur, to take over the reins of this session. And we have 2 very esteemed speakers, the resume or the bio sketch of which the chairperson will introduce to you. But we'll request Professor G.P. Rajashekar to say just a very few brief words on Indian mathematics, and then start an invocation and introduce the first speaker, the talk, and then the second speaker and the talk. Thank you so much. It's over to Professor Rajashekar. Thank you. Welcome. Namaskar. Professor Rajashekar, unmute yourself. Professor Rajashekar. Professor Rajashekar.
Yeah. Are you
Yeah, now we can hear you.
Are you able to hear me? Yeah. So good afternoon and welcome to this technical session 3, which is numeral system, Vijayanita and Jyamiti. We have with us Professor K. Ramasubramanian and Professor Clemency Montel. Let me introduce in brief. Professor K. Ramasubramanian is a professor at the Cell for the Indian Science, Technology and Sanskrit, Department of Humanities and Social Sciences, Indian Institute of Technology, Bombay. And his doctorate is in theoretical physics and MSc in Sanskrit and a bachelor's degree in engineering. This is just to illustrate the interdisciplinary nature of his diversified education background. Professor Ramasubramanian had good eclots. He had authored very popular books, and he was conferred with Vidvat Pravana, and he is also the fellow of the Indian National Academy, Indian National Science Academy, New Delhi. It's a pleasure to have Professor K. Ramasubramanian, and the second speaker is the other speaker is Professor Clemency Montel. He is currently head of the Department of Mathematics and Statistics at the University of Canterbury, New Zealand. She was awarded Fulbright Graduate Student Award and works in Greek, Latin, Sanskrit, Arabic at Brown University, Department of History of Mathematics. Her current research projects, History of Mathematical Tables, and she's also representative at International Commission of Mathematics since 2010 and Deputy Director of New Zealand South Asia. It's pleasure to have with us two eminent speakers on this technical session 3. So we are slightly delayed, but nonetheless, we'll be very happy to have this session. It's 2:46, so it's roughly 15 minutes delayed. So may I request the speakers to consider that and then keep the 15 minutes intact. So over to Professor Ramasubramanian and Professor Clemency Montel, please.
Clemency, would you like to start initially?
Certainly. We just need the slides. Aha. Greetings, everybody, from New Zealand, where it's 10:16 p.m. in the evening on Saturday night. So I'm very pleased to be co-presenting this presentation with Professor Ram. And when we were given the title, which was to include some very highlights of Indian mathematics over their illustrious history of more than 2 millennia, to include numerals and geometry and algebra, we immediately thought of a very notable scholar in the mid-second millennium, Nityananda, and a particular episode in a monumental treatise that he wrote called the Sarva Siddhanta Raja, the King of all Siddhantas, which in fact encapsulates many of the insights and innovations that were developed by Indian scholars to solve some of the most pressing problems in mathematics. So we will look at one particular excerpt from this text in which we see all these wonderful things being developed. So we could go to the next slide, please. Anna, you're on mute.
Okay, so I'm very delighted to present this work along with Professor Clemency Montel because we did this work together a few years back when I had a short visit to New Zealand. So this was a very interesting piece. We literally went through the manuscript, so spent hours and hours deciphering the text in the manuscript, and then we were really thrilled to know what the content has been, which is yet to be brought out, in fact. So we could look only a small section of this text, and that is what we will be presenting. Before I move on to provide an introduction, I wanted to spend a couple of minutes on the title, this Bharata-Tirtha. So this was quite interesting to me, and I was quite intrigued who coined this title. The word Tirtha literally means the water. Generally, that is the meaning that we take for Tirtha. So water has the nature of purifying things. So Tirtha literally means that which purifies. One can think of 3 kinds of Tirthas now. One is this Jangama Tirtha, which is a mobile Tirtha. The other is Sthavara Tirtha, that which is stagnant. And the third Tirtha is Manasa Tirtha. So when I say this Jangama Tirtha, in fact, people who possess this knowledge as they shed away the ignorance which we have, and thereby, with the knowledge pouring in the form of water, they are able to drive away the dirt in the form of ignorance in our minds, and therefore, the term Bharata-Tirtha is a beautiful term. So this is from the viewpoint of Jangama Tirtha. You have got people from all over the world. In the morning session, you had Gerard Huyet, so from the Europe, and now you have someone from New Zealand, so where the sunrise takes place for the first time. So anyway, so this is a Bharata-Tirtha, so those who have engaged themselves in their knowledge, they are shedding their waters to purify all our hearts. So the other aspect of this Tirtha, which is generally considered in India, is, so you go and take bath in a holy river like Ganga, and thereby you get purified. So that is the physical purification. So this is the mental purification that is happening through this process. So, and I'm so happy that this title has been coined for this. So having said this about the name of the whole webinar, so let me very quickly take you through the introductory part of our lecture. So India has a very, very long history of astronomy. So we have Aryabhatta, who is extremely famous, in whose name satellites have been launched. And he is the person who has provided a very solid background to what is called geometry among the available texts. So he has presented a couple of methods, but Aryabhatiya is a very terse text. So it presents hardly 2 verses for geometry, whereas our Nityananda, whose work we are going to present, would have presented almost 70-80 verses to discuss this science. So geometry literally means, so geometry, so I mean in a sense, so the terms are very similar. So geometry basically means miti is measure, jya is chord, measuring the chord. So since sign can be visualized as a chord, so that is the title geometry. Nityananda's presentation is quite elaborate, and can you move on to the next slide, please? There are a couple of interesting things which will come towards the end of the slides. So wherein he has presented a brilliant iterative procedure, and he also provides a beautiful method to solve a cubic equation. Next slide, please. Next slide.
Anuradha, next slide.
Yes. So we have, this is just an outline of the kind of history that we will very quickly will pass through. So around 1400 BC we have Laghada, then we have Shulvakaras, then there is a text called Vriddha Garga Samhita which is being studied now. Then we have Vararuchi's Chandravakyas, Aryabhatta, Varaha Mihira, Brahmagupta. Then we have Bhaskara, who wrote brilliant commentary on Aryabhatiya. Then we have Devacharya Lalla. Next, please. So this is to just give you a background of the kind of astronomers who have composed very important works. Is there a problem in moving from slide to slide? Okay, so then we have in this timeline, we find Govindaswamy, Mahaviracharya, and so on and so forth. Other famous astronomer is Bhaskara, whose work Leelavati, Bijaganita, and Siddhanta Shiromani are well known. And then we have this Kerala school in the 14th, 15th, and 16th century. Then comes Nityananda. So Nityananda, so I'm the 17th century astronomer. Next slide, Clemency, can you please take over?
Of course. So while we wait for the next slide to come up, Nityananda, we know a little bit of biographical detail about him, but we know he was the son of Devadatta and he worked at the court of Shah Jahan and flourished in the early 17th century just based on the dates of his manuscript. Can we have the next slide, please? Great. So he wrote the work that we will be looking at today is the Sarva Siddhanta Raja, and indeed this work epitomizes the style of many Sanskrit Siddhanta in this tradition. its technical content, the way in which it is arranged, and its style of composition that is in a set of hundreds and hundreds of verses written in various Sanskrit meters is very much emblematic of the Indian style of Siddhanta. So when we look at the Sava Siddhanta Raja, very similar to, say, a work of Bhattacharya in the 12th century, the Siddhanta Shiromani. So it would have been very familiar to the eyes of Sanskrit astronomers in terms of its composition and its technical content. However, it was incorporating many of the insights from other astronomers from all over the world. As well as the Sava Siddhanta Raja, Nityananda is known for two other works which were notably tabular works, that is, numerical tables that gave astronomical and mathematical data. One is called the Amrita Lahari and the other Siddhanta Sindhu. So if we just go to the next slide, please, and we'll have a look. We've actually got manuscripts of the Amrita Lahari. It's never been published fully before, so it's a project that remains for us. This, in fact, manuscript was brought from Nepal by a Japanese professor back to Japan and is sitting in the Tokyo University Library. So you can see it's written in this beautiful Nepali script. And true to the Indian tradition of the paper, such that the paper is longer than it is deep, we have the numerical tables that are oriented in a very interesting way. You can see if you can pick out, I don't have my cursor to show you, but you'll be able to see the 1, 2, 3, 4 running horizontally along the top of the page. And the numerical data for these tables actually hangs underneath. So the Amrita Lahari is very much a table in a Sanskrit format, but this was a relatively new genre for composition, at least tables that were aligned in rows and columns, and emerged in the beginning of the second millennium of the Common Era. The Amrita Lahari is very much what the astronomer needs to construct a panchanga, so it has tables of tithis, nakshatras and yogas, as well as oblique ascension and right ascensions, Gnomon shadows, and various chronological conversions of tables. So that was one of Nityananda's work, but perhaps the biggest one, even bigger by far, if we can have the next slide, please, is the Siddhanta Sindhu, the ocean of Siddhanta, Sindhu being the, have the next slide, please, which by contrast to this slide, the Amrita Lahari, which the manuscript is written very much in this landscape format, this book was in fact commissioned by Shah Jahan through his Wazir Asaf Khan in 1628. And it was in a massive set of astronomical tables, some 450 folio in length. And you can't see this in any detail, but there are millions upon millions of numbers that have been computed and written down in order to look up various astronomical and mathematical phenomena and being able to use them to compute the positions of the planets and again make compute tithis, nakshatras, yogas, and all sorts of other details that the astronomer needed to compute. So this is really a monumental work, and this, in fact, is from sitting in the library at the Jaipur Museum and preserved very beautifully with some beautiful elaborations on some of the pages. So really, Nityananda was very keen on the table genre and was very interested in how to compute tabular data. And in particular, we'll see this is very important when we look at the tradition of trigonometry. Can we have the next slide, please? So the Sava Siddhanta Raja itself is a very large work. Probably each chapter has around at least 100, if not several hundred verses in it. As is typical in the Siddhanta tradition, it's divided into two parts, a Ganita section and a Gola section. And the rationale behind the Gola section we will look at in the very next slide. But just to give you a flavour of the different topics that typically appear in these Ganita sections, we start off with an introductory chapter, namely philosophical rationales, then computing planetary longitudes and their first their mean longitudes, and then using orbital corrections, which are based on trigonometry, computing, the true longitudes and velocities of the planets. Then on to the Triprashna chapter, which has 3 questions. What time is it? Where am I? And what is the direction? Where is north? And then very notably, the lunar and solar eclipse chapters, and further on, other interesting astronomical phenomena that was important for various reasons, the elevation of the lunar crescent, conjunctions of stars and planets, and the altitudes of the stars and the planets. And the Gola section is much more cosmological and cosmographical in intent. There you find the rationales behind the configuration of the universe, along with astronomical instruments, including the armillary sphere. So you can see this is a really monumental work, both in its length and its scope, and is all the astronomer needs to be able to compute absolutely anything that they need to be able to fulfill the functions of their job. So one of the very interesting verses in the Gola section provides a rationale behind why all of this material is important on the next slide. We can have the next slide.
I'll take over. See, there is a very interesting verse which is presented right at the beginning of the Gola section. This is basically the second verse. So it goes like this. In fact, when I was in New Zealand, we even were thrilled to memorize these verses. Maybe we can even, she can also join while I read the verse. Yat kinchit ganitam grahasya ganako janan vinavasanam prishtasanna pare nagola vidusha prashna prapanchoktibihi brut kim brute pratitam taduttaramayam golagamatnyo yataha tasmat gola vichara charu rachanam Okay, very good. So this is a nice verse which basically presents the importance of knowing the rationale. Normally, in Indian astronomical texts, they just give the rules and then they are moving ahead from rule to rule. But we find a few works which also deliberate much on the rationale. And this Nityananda's work is an outstanding work in that viewpoint, and so too this starts with much earlier in this tradition, but not in the main text but in the commentaries. So Bhaskara presents detailed rationale in his commentaries, so though not much in the text. Nityananda in the text itself presents very detailed vasanas. The vasana basically means rationale by which a certain principle gets lodged into your mind. The term vasana is used in philosophical literature also. Any kind of impression that you carry with you is called vasana in a more generic sense. So here in the mathematical context, it essentially means rationale. Once the rationale is understood, then the principles get deeply lodged into our mind and we may be able to construct whenever we want. So what he says is, Yatkinchit ganitam rahasya ganakaha janan vina vasana. If somebody tries to just to do some sort of a computation without knowing the rationale behind, then when he goes into the assembly of scholars and if he is going to be questioned by other scholars, then what is it that this person can reply? So he will be showing a shameful face in order to save those people. So Nityananda says, I am trying to present the vasanas in this text, and by reading this text, you will be able to shine like a star in the assembly of scholars. That is what he is saying. Say, Tasmat gola vichara charu rachanam vakye satam pritaye. So in order to please scholars, so I am just presenting the rationale, so which is behind the astronomical procedures which have been described in the Ganita section. So that is what is the sum and substance of this verse. In fact, he starts with this, and then there are a few more beautiful verses. In fact, the next verse he will just say, so if you have a beautiful house, fantastically decorated, but if there is no light, so how can one enjoy that? Okay. So if someone is looking very beautiful, but she is not intelligent, then what is it that you are going to gain by marrying her? So there are a few examples with which he is trying to impress upon the importance of Gola. In fact, that goes in the next verse. So anyway, we will not get into that. Can you just move to the next slide, please? So Nityananda, yeah, you can take over perhaps.
Okay, so we'll go from the Siddhanta Raja as a whole to the particular section that we're interested in, which is 60 verses or so. This is the trigonometry section. Now, of course, when we look at the legacy of Indian scientists throughout history, trigonometry is big there to a huge contribution to the world and mathematics in general. But very interestingly, trigonometry was seen as part of astronomy for the longest part, precisely because of its application towards correcting planetary positions in terms of the various cosmological models that they had. So we find this exposition, this very mathematical, theoretical exposition on trigonometry, not in its own chapter on mathematics, but buried inside a chapter on spashta, or the true longitudes of the planets. Because those, in order to find the true longitudes, the corrections that you need to put to the mean ones are based on trigonometry. So thus it's necessary for the astronomer. So you'll see a very dense and thorough description of the various rules of trigonometry, whereas Nityananda's predecessors had very much given the rules or the actual sign values themselves very concisely in just a handful of verses. Nityananda really gives us a thorough explanation of all of the rules that we need to be able to build our own trigonometric table. So he's got tables in his mind, just like we see that was a medium, which was one which he composed many works in. So you will see, he gives us a set of rules to find the signs of various distinct values, the sign of 90, 30, and 18 degrees, as well as several rules to find double or half the arc, and to find the famous rules for the sum and differences of two arcs. But then he doesn't just stop there like many of his predecessors had. He, in fact, used geometric construction and algebra and some very, very interesting iterative techniques, not only to prove these results, but in fact to determine the sign of 1 degree and the sign of 1 minute. So here's a page from the manuscript, one of the manuscripts which you can find at the Rajasthan Oriental Research Institute, Rory, which shows some of the verses that we translated and looked at. We had multiple manuscripts, so we could compare and contrast the various scribal errors and make sure we had a correct text. But what you'll notice about this particular page here from the manuscript is we have these wonderful diagrams which show us the very geometrical ways and graphical ways which we may derive various particular sign values. So can we have the next slide, please? Professor Ram, do you want to take over?
Yeah. Okay, fine. So this, she was showing a slide in which you found some nice diagrams. Now what you see in front of your screen is a slide wherein you find quite a few equations. So you see, in dealing with mathematics, what happened? So in dealing with mathematics, so you may have to even jot down the equations, however describes doing this. So for instance, if you just see this Yava, so in the first line, if you are able to see that, then it basically represents some algebraic equation. So this is how they were writing down the equations. And to optimize the space, see today we have the luxury of using as many pages as you want to scribe and throw away. But in those days, getting paper was difficult, writing was all the more difficult, and you had to somehow optimize the kind of resources that you had. And they were just writing down the equations just in the line. And also, we should be aware of the fact that once you write something there, so there is no way that you will be able to cut. So people should have been extremely careful, and the scribes, so fortunately, have been quite cautious. Though of course there will be a few slips here and there, but they have been really careful. And some of us who are faculty members, we know how the documents are produced by our students. Okay, so let us move. Next, please. So after that, so we will just move on to the computation of sine itself. So the verse that you see in front of you is the introductory verse which Nityananda gives to the whole chapter of discussion on science. He says, Acharyavarya ganakastayeva janantiye jnanayanopapatti tatodhigantum padavincha tesham mahajado vanchati madrishopi. So this is a way of expressing his humility. So Nityananda calls himself Mahajada. So, you know, Mahajada means supreme dullard. Okay. Mahajado vanchati madrishopi. So basically what he wants to convey here is Acharyavarya ganakaha tayeva. Only those people are considered as mathematicians who actually know how the sine tables are really computed. Jnanantiye jnanayanopapatti. So today most of us make use of various software, so we don't know what actually runs behind. So if you need to compute sines, you just press a button and you get it. So what is being done by the calculator in order to get the sine value is something which is hardly known by many of us. So here what is being said by Nityananda is, unless you know the mathematics behind how it is being computed, you cannot be declared as a mathematician. So Acharyavarya ganakaha tayeva. Tayeva means only those can be considered as mathematicians who actually know the rationale behind what they are doing. So then he says, in order to elevate myself to the status of a mathematician, so I am trying to provide you the rationale, so by which you can judge whether I qualify or not. So that is the content of this verse. Next, please. So this is how he starts, and then he moves on in a very, very systematic manner to present the derivation of sines at various levels. So this slide basically gives you an introduction to the sine, how it is computed in Indian astronomical texts. So if you look at this diagram, in the right hand side, you see an arc BC. So BDC is the arc. That arc basically looks like a bow, as you can see. So therefore, the term which is used is chapa. So chapa literally means bow. So chapa is the arc, and what you need to find out is basically, so the chord BE. Okay, BD is the arc and BE is the semi-chord. So the chord looks like the string of the bow, and therefore the name that is given in Indian astronomical works is basically string. Jya literally means string. So you can use the word Jya, you can use the word Maurvi, you can use the word Guna. So all synonyms are employed by astronomers. So depending on what is required in the verse, so to meet the metrical requirement, they may be using one of these synonyms. So BEC is the Jya, BDC is the arc. So the problem is essentially to find out what is BE corresponding to BD. So this is the problem. And if you look at the other terminologies, ED is basically called as a Shara. Shara is basically arrow, so which you can easily understand. So if DE is sine, AE is going to be cos, and EG is going to be radius minus cosine function, which is basically verse sine function. Okay, next please. So this is the background that is required for us to understand. Would you like to take over?
Certainly. In fact, maybe for interest of time, we could skip this one and maybe go to the next one.
Okay, go to the next one.
Next slide. So the question while we're going to the next slide is, how many sines can you compute using this geometry? Of course, when we're taught sines today in modern schools, we're taught sines as very much as the ratio of two quantities, the opposite or the adjacent or the hypotenuse. But as you can see, very much this is the question. Given an arc, what is the corresponding segment corresponding to that arc? So questions could be answered, questions such as that could be answered by just using geometry. Can we have the next slide, please? But geometry will only take you so far. So for instance, you can inscribe a hexagon in the circle, you can inscribe a square in the circle, you can inscribe various geometrical entities and get various right-angled triangles to be able to find sines, but geometry will only take you down to the sine of 3 degrees. That is, if you're looking for a table of the signs in a quadrant, degree by degree, you cannot get there by geometry. And this Nityananda alludes to in one of the introductory verses to the signs here. Well, just won't, in interest of time, won't look too much at the verse, but you can see now he says, I'm going to give you the rationale behind the computation of the signs, since there are only 30 signs. And by that he means, using geometrical methods that I will outline, you can only get down to the sign of 3 degrees. If you want to find the sign of 1 degree to any accuracy, you'll have to use another method, an analytical method, to be able to compute it. You can, of course, take the sine of 3 degrees and divide by 3, but that's not terribly accurate. But we'll tell you the very ingenious way in which Nityananda expounds to find the sine of 1 degree. Next slide, please. So you can think of it, next slide please, as some various tools that are in the toolbox, and we'll just have a close-up on this beautiful diagram in the manuscript, that some of the signs are very easy to find geometrically. For instance, the sine of 90 degrees is just the radius. The sine of 30 degrees, if you imagine a 30, 60, 90 degree triangle, and in fact you're looking at inscribing a hexagon in a circle, you'll find that the sine of 30 is the radius of the r over 2, and the reason that we use the radius here is, of course, the radius, unlike modern times, is not just set to 1, but a circle of any radius that you like. For various scholars it was 3,438, that was Brahmagupta's value and Bhattacharya's value, but for others, Bhattacharya and his Karana has 120 for the radius, and for others, indeed for Nityananda, the radius was 60, just a very useful amount for sexagesimal computations. The other ones you can find geometrically directly are the sine of 18 degrees and also the sine of 45 degrees. And again, this is just simple geometry, basically using similar triangles and playing with the Pythagorean theorem to be able to find the results there. And I'm sorry, I don't have the cursor, so we can't really point more precisely to the bits and pieces. But from, of course, once you've got the sine of 18, then you've got the sine of 72. Once you've got the sine of 36, of course, you've got the sine of 54, and so forth and so on. So this is building the sine table, not in order of, going 1, 2, 3, 4, 5, but in order of what the geometrical constructions will do. Now, we need a few more tools in our toolbox. We need a few more rules to be able to generate some more slides. Can we have the next slide, please? So Nityananda then has a beautiful verse which describes a rule which is written in this beautiful metrical poetry for finding the sine of half and double the arc. And we'll just wait for the slide to be moved. And of course, this is our very familiar half arc formula or double arc formula. Can we have the next slide, please? There we go. Only it looks a little bit foreign to us because instead of using the cosine, it's using this somewhat archaic to our eyes now, the versed sine, the verse sine here, which is the radius minus the cosine of theta here. So very easily, once you have this rule where you can find the sines of either double the angle or half the angle, you can go from the sine of 72 to find the sine of 36, to find the sine of 8, to find the sine of 9, and of course halves of that, so 4.5 and so forth and so on. From 30 you can go to 15, so you're adding, using this double angle formula or this half arc formula, you can find many more sines, but you need at least one more rule to be able to find some more, and this is the really famous sums or differences formula that was first seen in Bhaskara's Siddhanta Shiromani. But Nityananda has a particularly beautiful verse. Well, he has a pair of verses which are almost identical, apart from just a few syllables, that give us the rules for the sine of the sum of angles and the sine of the differences of two arcs. Can we have the next slide, please? And here it is. Now you can just see, if you look very closely, that the differences have been highlighted in red and blue here. Professor Ram, would you like to take over?
So this verse basically gives you the sine of theta plus phi, as we call today, sine C plus A plus B kind of a thing. So how does the verse go? This is composed in Arya meter. Anyonya koti murvya kunite ye cheshtachapayor durje trijyor dhrite tayor yaha yogassa chapayogajya. So chapa basically, as I told you, is arc. Chapa yoga means you have two arcs and the sum of two arcs. So if you have an arc, so that will have a sign. If you have one more arc, that will have a separate sign. If you just add these two arcs, what is going to be the sign? It is not basically the sum of those two signs will give you the sign. So what is the formula? So he says, Anyonya koti maurvya. Koti basically means cosine. So koti maurvya, Anyonya means consider two angles theta and phi. So take the cosine of the other angle, multiply with the sine of this angle. Take the sine of this angle, multiply with the cosine of the other angle. So and then he says you have to divide by trijya. Trijya basically means r. So this has to do with the dimensions. So don't worry about. We have used the S and C so to represent that there is an r in the numerator also. So that is all. Trijyo dhrite tayoryaha yogaha sa chapa yogajya. So how does he give the difference formula? You find the same thing. Obviously the numerator is going to be the same. The only thing that will reverse is basically the plus and minus. And therefore, you see the same verse has been used. Instead of yoga, you have vyuti. Instead of this, towards the end of the verse, again, yoga is replaced with vivara. So that has to do with the metrical requirements. That is all. Next, please. In fact, this is a much more beautiful thing which you do not find in any of the texts. As far as my knowledge goes, I'm sure Clemency also would agree with that. So we are quite thrilled to read this. So this is basically a graphic description of how you have to go about constructing the geometrical construction that are required for you to prove the result. So this verse goes like Kakhagagham bhumitaleshu mandalam nakendrakam karkatake nasadhaye Kacham chacham chapayugam kangam changam changam kramat vyasadalattrayam likhet. What does he say? He says, today we will say, so construct a line AB, draw a circle ABCD. So instead of that, he is using kakhagagham. Okay? Kakhagagham. So kakhagagha. So that is the circle. Bhumitaleshu mandalam. Mandalam means circle. Where is it centered? Nakendrakam. And how do you draw the circle? Through a compass. Karkatake nasadhayet. Then he goes on in the second half of the verse. Kacham chacham. So ka cha is one arc. As you can see in the right hand side diagram. Ka cha is one arc. And then he says chacham. Chacha is the second arc. And then he says you may have to draw. Okay. So a line between cha and ga. That is what kangam. You have to draw three lines. You see. So he says kangam, changam, changam, kramat. In sequence you draw all these lines. Vyasa dalatrayam likhet. In Sanskrit, Vyasa has various meanings. So we know the Veda Vyasa. And Vyasa basically means the one who divides. In fact, Veda Vyasa, who is supposed to have given 4 Vedas, is supposed to have divided a huge corpus into various parts. Therefore, he is called Vyasa. And in mathematical texts, the term Vyasa is used to refer to the diameter, because the diameter is something which splits the circle into 2 halves, and therefore it is called Vyasa. Vyasa Dala means half of the diameter, which is basically the radius. So he says draw 3 radii. Next please. So this is how you find a beautiful description of how you have to go about drawing the diagram. So in the interest of time, I will not be reading the verse. So here he further says, see, chajam, chajam. So there are Sanskrit lovers I know. So here, chajam, Joyson itself was a Joyson. Chajam, chajam. So this is all, if you see in the diagram, so these are all the signs. Chapa yugas yadurjyake. And how you have to do that? He says, drop a perpendicular from cha, that will go and meet at ja. Drop a perpendicular from cha, that will go and meet at ja. So these are the 2 signs. What is it that you have to determine? you have to determine the perpendicular that is dropped from cha to ta. Okay, so all that is beautifully narrated in the verse. Kange lambavadeva patite. Lambavadeva patite means, so just like a plumb line, you understand? So in order to say that you have to drop a perpendicular, they will say, as if you keep a plumb line wherever it will go and meet. So that is the point that needs to be marked. Okay. So then the question is, how do you determine chata? I think we may have to rush fast. Quickly change the slide, please. We can keep on rolling the slide every 2 minutes. So whether we stop or we don't stop. Yeah, maybe 1.5 minutes. Yeah, so these are all various descriptions that you find there. So next slide, please. Just move on. Yeah. Clemency, would you like to say quickly?
So quickly, we don't have time to go into the technical details, but it's all set out in a paper that we wrote if you're interested. But I think really we can't underestimate the detail in which Nityananda goes in, who actually provided geometrical diagrammatic validation for his result, and also this use of lettered points, so mediating between the text and the diagram by actually incorporating the points as though they were a Sanskrit word, which at first really led us scratching our heads. But of course, as you can see, it's a perfect way to identify these points on the diagram, which hadn't been done, which was a relatively new thing in Nityananda's time.
Yeah, next please.
So what he's trying to do here essentially is show the sum formula, the sum of two arcs. So what he's looking at the arc, which you can see is represented by the red arc delimiter there, and the black one. This is, you can think of theta and phi, and the sum of those arcs is actually equal to the line cha ta, which is what he's actually trying to find an expression for. And cha ta he is dividing into two pieces, the small line segment cha ta and the second one ta ta. So using various identifications and similar triangles in a very ingenious way, ones that had us scratching our head for quite a while, he's actually able to find expressions for both of these and thus derive the sum formula. And he has exactly the same type of approach for the difference formula here. The crux of the matter, next slide please, actually relies on showing that the equivalence between the sine theta, which is cha ja, is actually the same as the line segment ja ta, which if you just think back to the diagram what it looked like. And this involves some fairly heavy algebra to be able to show this, which Nityananda steps us through very carefully by alerting us to the various similar triangles in the diagram by reference to their lettered points and showing their similarities. Can we have the next slide, please? So he, in fact, shows us that ja pa here, which is equivalent to this ta ta, one of the line segments that we need, is equal to the sine theta cos phi over r. And you can see this is just 1/2 of the sum of arcs formula. And in a similar way, using Pythagorean theorem and similar triangles, he can tell us how much cha ta is. Next slide, please. So all of this is absolutely incredibly done, not by recourse to using thetas and sines and x's and y's and symbolic styles of reasoning, but worked within this very beautiful verses in this metrical content. This is really where the real genius lies here. Next slide, please. So this is, so very carefully in a verse here, he explains how this side ja ta, which he's looking for, is in fact equal to the same side cha ja, and that's the crux of being able to derive this the sum of two arcs formula. Again, the technical details are carefully stepped through with their verses in the literature that we have written. Next slide, please. But Nityananda doesn't stop there. He decides not only does he want to show this algebraically, or at least diagrammatically, working through with similar triangles, but he's actually going to demonstrate this by means of a geometrical construction, which he uses by the word shilpa, a very interesting word which typically can mean to refer to architecture or diagrams, but here very much it means almost a visual geometrical validation of the particular result. And it's just wonderful. The scribe, in fact, has tried to reconstruct not terribly badly, but it'd be interesting to see if he really used a karataka or was doing it by hand to be able to validate the equality of these two line segments in which the whole demonstration rests. So next slide, please. Using a verse, which is given up here, which perhaps Professor Ram, you can take over, he explains the way in which this can be derived.
Okay. So here, what you find is, there is an echo. Okay, so Karkatakena Jatabhyam Timina Tulyatribahukam Kritva Bahiriha Kone Dhrutva Ganga Jatadik Prasarite Rekhe. So this is a beautiful verse. So you see, what he says is Jatabhyam. Jatabhyam means, so usually Jata means something with a matted hair, but you should not understand it as a matted hair. Ja and Ta here basically refer to 2 points here. So that in the line that you find horizontal line, you find Ja and you find Ta. Around these 2 points you have to draw a circle. Timina tulyatribahukam kritva. So basically means you have to construct some similar triangles. So tulyatribahuka basically means so equilateral triangles. 2 equilateral triangles have to be constructed. So he gives all the details, so which is extremely rare to find in any of these texts. So this kind of minute details as to how you have to go about drawing diagrams is something which is phenomenal. So next, please. So he just shows through this meticulous way of drawing. Next, we can move on. So this is all details. So this is, but for this diagram, it would have been extremely difficult. Though this diagram is not so beautiful in the manuscript. So we have been struggling for about a couple of days how to figure out, and finally we managed, and it was an aha moment for me and Clemency when we discovered this. Next, please. Next. Okay, so would you like to just take over? Yeah.
Okay, so now we just to recap. We've got all the geometry that we need to be able to find 30 sines, all the way down to the sine of 3 degrees. So the idea is you've got the sine of 15, you've got the sine of 9 degrees, you can take the difference of the sine of 15 and 9 and to find the sine of 6, and then you can use the half angle formula to find the sine of 3. And then you can keep doubling that, so you've got the sine of 3 degrees. But of course, Nityananda says, what say you need the sine of 1 degrees? And that's incredibly important. What do we do then? And for that, he comes up with some ingenious method that is not based on geometry, but based on an analytical recursive iterative procedure, which he explains to us in the next verse. We know that he did this, although he doesn't actually give us the value in his text at this point, he gives it to us in the tables, the Siddhanta Sindhu. Can I have the next slide, please? Oh, which we do we have? Next slide, please.
Next.
And here we have, if we just keep the next slide, which is a close-up of this particular table. This table is a table of sines and their differences down to minutes of arc. So even between 0 and 1 degree, there are 60 values, well, 120 values because there are their differences as well. So this table has 554,000 entries that have been computed and copied down. Really, if we think about it, it's really weapons of mass computation we might talk about. You know, we're talking about serious mathematical exertion here. So if we go to the next slide, what we're interested in here is the sine of 1 degree. What is it?
Next slide.
Next slide. And if we just look here right in the middle, I can't point it out with the pointer, but you can see you've got the sine of 0, 0, which is 0, 0, 0, 0. But if we go across to the right, we've got the sine and reading downwards, 1, 2, 49, 43, 11. And this is a very accurate value to the sine of 1 degree. It's not obtained by taking the sine of 3 degrees and dividing by 3. It's instead solving a cubic equation by means of an iterative algorithm. And just as we finish off, a very quick description of that cubic equation that you need to solve to determine the sine of 1 degree.
Next slide. Yeah, next slide, please. You just move on quickly. So we know that, so this is basically the cubic equation which most of us would know, the sine 3 theta is 3 sine theta minus 4 sine cube theta, is a relation which we study when we study trigonometry. So from this equation, he just moves on to just define, and then you will see that at the bottom of this slide, you have an equation. So we just use this notation y for representing sine of 1 degree, and we have an equation, cubic equation, that is to be solved. Move on to the next slide, please. So this cubic equation, so how does he go about solving? So this is something which is done in 2-3 ways. In fact, around the 15th century, there is a brilliant mathematician called Al-Kashi, so who has attempted to solve this, and he has presented a certain method. What Nityananda does in his text is basically beautifully paraphrasing what Al-Kashi has done. He has also presented another interesting iterative procedure by which one will be able to solve. And what you find in this slide, which is being projected to you, is the value which has been stated. You see, so Rama means 3, Naga means 8, Jina means 24, and Deva means 33, and so on and so forth. This is basically presented to you in what is called Bhuta Sankhya system. Okay, so a Bhuta Sankhya system is one of the systems that has been adopted by Indian astronomers to represent numbers, as they have to integrate the numbers along with their beautiful metrical composition. So therefore, some of them have used the Bhuta Sankhya, some of them have used Katapayadi system. So what is to be noted here is, so this 3, 8, 1, 2, 3, 4, 5, 6, 7, 8. So this is 8th sextodecimal place. Can you imagine? So the kind of accuracy which they were trying to determine. So that intention is what is something which is really remarkable to be appreciated. So we find the last value to be 50. And how is it given? So if you look at the last entry, Biyad Banaha. Biyat means space, which represents 0, and Bana represents 5. Okay, Pancha Bana. So that is how the last value is given. It starts with Rama and goes on. Next slide, please. So when we did, what we did was, we actually tried to compute this numerically by, can you go to the previous slide? One thing got slipped, I think. So just to show, so this is an iterative thing. So you see, you find an equation yn is equal to, you start with a certain approximation, you just keep on doing that iteratively. And next slide. So once you do this, by iterative method, you try to solve. As you can see, it is extremely fastly converging. So in the first row that you find 1, 2, 48, 11, and so on. And the difference, if you see in the third column, so it just drastically reduces. Within 5 steps, you are able to get to the 8th sexagesimal accuracy. Whereas in the other method, so if you have to do Al-Kashi's method, so to get the 6, you may have to do a lot more work. So it is far more efficient algorithm when it comes to, and why it converges so fast? So because there are a lot of mathematicians, one can just say that it could be something like close to the fixed point iteration technique. Next, please. And this iterative technique has been extensively employed by Indian astronomers at various stages. So this is basically described in about 20-25 verses. So we don't get into the details of this. Next slide, please. So Clemency, can you just quickly say on something on this?
Certainly. So part of the way in which this iterative procedure is described and set out is using algebra, and very much in terms of this quasi-symbolic expression. So you can see at the bottom of the screen the way in which Nityananda sets out what we would consider to be 3y squared plus 2by minus b squared all over 4. You can see the Yava. The Ya is literally what we would recognize today as X, from Yavat Tavat, meaning whatever, however much you want. So that's the unknown there. The Va is a shorthand for Varga. So it literally means y squared. The 3 is the coefficient, so we get 3y squared. Then we've got Yabu, and Bu is the base of this. We've represented it with B in our modern notation. So very easily, Nityananda is able to use this notation that he's got, 2by, and minus b squared again, Bu Va, short for Bu Varga, and 1 with a little dot over the top of it. That dot means subtract. So that's why we've got the minus b squared there. And for some reason, the 4's gone missing at It might be the scribal mistake, or it might have just got left out of the diagram. So this beautiful symbolic algebra that Nityananda is actually incorporating in his text to use algebra to be able to derive the very algorithm to derive this cubic, for which he applies this iterative technique on. So there's algebra for you, seen in a text which is doing some fairly sophisticated mathematics to find an equation for which to derive the sine of 1 degree. Next slide, please.
Yeah. So basically, so what we find in Nityananda's text is, so this systematic exposition of the sine function, starting from the basics. So how to go about in about 60 verses is something which is extremely difficult to find in any of the other works that we have seen so far. So one is this very, very systematic procedure. And the period in which it was composed is basically around the 17th century, when we had this Islamic rule over India. So during this period, so there are a lot of works which got composed, which also reflect what has been done in the other tradition, Islamic tradition. Some of these Sanskrit works, they have beautifully paraphrased what has been done by the Islamic astronomers. Al-Kashi was a brilliant astronomer who had found a brilliant way of solving this. So as I was mentioning earlier, so though Al-Kashi's method is quite ingenious in its own right, so it is quite laborious as far as arriving at the accurate value of sine of 1 degree is concerned. So there are different techniques, as we know, so to solve the same problem. So that has been attempted there, and Nityananda, having seen that, so he tried to adopt a certain method which the Indians have been quite familiar, so in various other contexts in astronomical solve problems. So he tried this iterative procedure, which seemed to have given extremely fast convergent ways of arriving at this value. So interestingly, the method which has been given by Nityananda, in 5 iterations you can do, in contrast only by 10 in Al-Kashi's method. So that is how the fast convergence happens. This is some interesting observation which we made as we were trying to work on this. The numerical computations done by Nityananda's method are far simpler. And next slide, I think more or less we are done with. Okay, so we had a couple of papers on this. So we had a lot of joy in trying to figure out from the manuscript and try to present in the form of algorithm which can be understood by today's mathematicians. So it was a pleasure that both of us got invited to present, and we chose a work which could give you a flavor of how algebra was done, how geometry was done, how the numbers were being played around. So with this, I think we thank the organizers for giving us this opportunity. We'll be very happy to answer any questions.
Thank you very much.
So thank you very much, Professor Ramsubramanian and Professor Mankalle. Over to my colleagues, Professor Jitendra Kumar and Professor Swanan Khare for a question. Professor Jitendra and Swanan, are you able to hear me?
Yes. Thank you, Professor Clements and Professor Ramsubramanian for wonderful lectures. So there is one question where the observation is made that in order to understand the mathematics hidden inside the shlokas, one needs to have a very good expertise on Sanskrit literature also, because the way you are explaining the shlokas, there is this very beautiful way in which you can use the Sanskrit language and use different words for the same entity. And in order that you put that in a meter, so from linguistic point of view also, if you want to do this, there is a big challenge. So the questioner wants to ask how difficult was it for you to go through these? And in general, if one wants to read the shlokas and want to interpret them, How would one go about it? Can you?
Yeah. Okay. So this is something which we need to understand, that it is a technical literature. After all, any technical literature, one has to get familiarized with those technical terms. So when you want to study physics, so the momentum, so the virus, whatever it is, chaos, etc., whatever we use, so these are all technical terms in those literature. So you have to first get familiar with the technical terms. And that would definitely take some time, yes. But having said, there is a real charm and beauty in presenting something in the form of poetry. So poetry adds beauty. So though we didn't have time, so myself and Clemency, we would have spent hours when we drove, so chanting these beautiful verses and trying to commit to memory. So that itself is a real beauty. And we do have a fantastic memory, even today morning session. So I was just partially listening to. So when Amba Kulkarni was mentioning that 4,000 sutras we used to memorize in 6 months, even today, okay, forget about those days. So there are Pathashalas. So our ability to memorize is something which is phenomenal, but somehow we have got lost. So the familiarity with the language, yes. So unfortunately we didn't study Sanskrit and therefore it looks difficult. So if somebody did not know Germany, so I assume 100 years before, when some paper was written in German, so what would you do? You have to struggle hard and then learn Germany and then only learn what has Einstein done, what has somebody else done. So this language is something which is far more easy for Indians because most of the local languages also have those words. So they have borrowed these words. So one need to. So as far as my own experience is concerned, though I have got training, so right from the beginning, there was some time which was required to get familiar with the technical terms. Okay. So and in fact, look at the other presenter, so Clemency, who is completely from a different country, where till her graduate, she would not have known what is Sanskrit. Okay. So, but then she has picked up, and so it is a question of interest. So that is all it is.
Yeah.
But I have to add, it's rather ironic that Nityananda starts this section by saying, I'm explaining this very carefully for the Mahajada, right? The Dala.
Yeah.
So really, we found it very difficult to read it ourselves. We thought we were the super Mahajada. We were the super Dala.
So do we have another question?
I think, one more question. Professor Shailendra Varshney has asked a question. I think partially you answered already, Professor. But I'll read the question. The question is that what happened from 16th century to 19th century? Why such scholarly work couldn't progress during that? So
yeah,
I think you answered.
Yeah, I'll give you a short answer. So there was a lot of turmoil. So this work, Nityananda's work, in fact, I was quite thrilled when I read. I must tell you that, see, there are works in which you will use only some simple meters to compose. Whereas, so starting from Bhaskaracharya and even before earlier, so Aryabhatiya, for instance, is composed only in Arya meter. That gives you a lot of flexibility. Whereas, these people have composed verses in a variety of meters which will be extremely appealing to us. Now, what happened was, so there have been a lot of invasions, and in spite of this, so this tradition continued. And we had scholarly works which have been composed even as late as 17th century. There are works which have been composed even much later in mathematics itself, so till 18th, 19th century. The Orissa astronomer, for instance, has composed a text, so which has thousands of verses. So this tradition continued, but so there was a serious problem in continuing the knowledge the way it was passed on from generation to generation, because the whole system got somewhat disrupted because of certain other rules, alien rule which was trying to impose various kinds of restrictions. I'm not getting into the details of all that, but so that is one of the reasons, definitely. all said and done, there has to be a conducive environment for scholarship to flourish. So if that is not provided, number one, it is not provided is one aspect by the state. Number two, you lay your hands on the way the system is functioning. This is far more disruptive. So one is encouragement. And the third aspect is any scholarship can grow only when the society receives it. So if all the three are not valued, so then I think there is a serious problem in building the scholarship. So in spite of all this, that we are able to get these manuscripts preserved is something which is really a great blessing. So that is all I would say. So though our government has not done after independence too much to really build a scholarship in studying these manuscripts, still there are some pockets which people have been preserving as a great resource and treasure at the family level. So fortunately, we are having them.
So I think due to lack of time, we may have to close the session because I think I see another chair is waiting. So I take this opportunity. The lecture started with a brief history of Vedic mathematics. Hello?
Yes, yes.
Sorry, can I continue?
Yeah, proceed.
So Vedic mathematics with the timeline of scholars, and then it narrated little elaborately on Nityananda's contributions, in particular computation on science, etc. And it clearly indicates how such a complex computations are hidden in a very compact slokas. So this is a very unique Jugalbandi of Sanskrit and Vedic mathematics by Professor Ram Subramanian and Professor Clemency Montelli. So we take this opportunity to thank Professor Ram Subramanian and Professor Montelli for kindly sparing their valuable time and delivering a wonderful lecture. On behalf of IIT Kharagpur, we thank you one more time. Thank you very much.
Yeah, this Jugalbandi was done by people who are separated by 12,000 kilometers.
Yes. So over to Professor Johnson.
Professor Joyson? Professor Joyson?
Yeah. So can I
Could I just add a small word there?
Sure. Yeah. So I think
I would just...
please.
We can't hear you. We can't hear Professor Johnson.
Can you hear me?
We can't hear what you're saying. But in the meanwhile, I just would want to express a special gratitude to Professor Ramasubramaniam and Professor Clemency Montel, who were instrumental for the start of the course History of Science and Technology in Ancient India at IIT Kharagpur. So they're coming here in 2017 in October and doing a very engaging workshop with over 100 students and some faculty members is what led to the interest of the generation of that course and many other things. They kept coming back to help us initially, and now we hope that they'll come back again in the future. And if I may, so thank you very much. Well, dhanyawad.
Thank you.
Can you hear me right now? Can you hear me right now?
Professor Johnson, we can't hear you still.
Okay,
No, we
so
can't.
on behalf of then Professor Joyson, let me close the session, and once again, thank you very much for your valuable time. Thank you.
Can you hear me right now?
Yes.
Okay, I
Yes.
think Ramji and Madam Clemency, I'll put it this way. I think I'm a small musician, so for me it was a jugalbandi of the sitar and the sarod. Like Pandit Ravi Shankar and Ustad Ali Akbar Khan, and the raga is Sindhu Bhairavi, and I found a lot of mathematics within the poetry, because poetry is rhythms, and rhythms are proportions, and proportions are the sequencing over space and time, and that is again back to mathematics. So I think the wonderful work that the two of you have done opens up a great platform for all our future scholars to decode, unlock, and decipher the great talent which lies in the bosom of our Indian mathematics, which of course had gone through different roads to different parts of the world. One, of course, was Arabia in different times. Once was during the times of Baghdad, Harun al-Rashid, and second time when the Mughals came to India, which Ramji and you have said so well. So I think this was really a great platform, truly a brilliant session. And with this, yeah, thank you. And
Thank you.
Thank you, Ramji, and thank you, madam. And I think sooner or later, we are going to have a center for Indian knowledge systems at IIT Kharagpur, Center for Excellence. So I think your presence is of paramount importance in the days and the months and the years to come. You know, to come and guide us, to come and guide us and create a niche from Vedic mathematics to its application in contemporary mathematics. The whole continuity. The whole continuity.
See, there are people in whose name itself there is joy. We have Swanand, we have joy. So we will have great joy when we come there, no doubt.
Thank you. Thank you so much. So I think really a pleasure. Pranam Ramji, Pranam madam. Yeah, and Professor Montele. So with this we move on to the fourth technical session, or the final session for day 2, which is Rasayana, which is another brilliance of India, Yoga Kshema Bahama. Look at both the sides, the spiritual and the material sides of living, livelihood and existence. And we have a galaxy of people also in this session, and this session will be chaired by one of our most brilliant professors of chemistry, Professor P.K. Chattaraj, Professor Pratim Chattaraj. So it will be his pleasant duty to introduce 2 great stalwarts on Indian chemistry who has looked into the depths of the various, the mysteries and the demystification of Indian chemistry from the deeper side to the more expressive side. And the 2 of them are Professor B.M. Dept and Professor Shomoresh Bhattacharya. And the whole session, the last session of today, will be supported by 2 great rapporteurs. One is Dr. Shubhoshachi Mishra, and the other one is Dr. Anu Ayappan. So with this, I really have a great pleasure to hand over to Professor Pratim Chattaraj to take over the mandate of this session. So over to you. Yes? Yes? Anything?
Professor Joyson, just if I may.
Yes.
Okay.
Professor Joyson.
Yes.
Yeah, I also would like to mention that Professor Pratim, we are very fortunate at the History course that Professor Partha Pratim Chakraborty is one of the most regular teachers on that course. So we are extremely grateful to him for always making the time to come and teach this course for us every semester. So I just wanted to put that in on record for everybody to...
no, there is a little correction. I am not Partha Pratim, I am just Pratim. Can you hear me?
Sir, yes, we are very grateful to have Professor Pratim Kumar Chattaraj.
Professor Pratim.
Yes.
Yeah.
Yes, Professor Pratim Kumar Chattaraj.
Yeah.
So Professor Pratim Kumar Chattaraj teaches Rasayana in our History course.
Right.
And we are very grateful to him for that. Thank you.
So over to you, Professor Chattaraj. Kindly take over the session.
Okay. So first of all, I would like to thank both Professor Sen and Professor Chaudhary. Good afternoon, friends. Now, welcome to this session on Rasayana, the chemical sciences. Hindu Rasayana, as described in Vedas, has a checkered history. Unlike other branches of science, such as physics and mathematics, chemistry was not considered in the same footing owing to its connection with religion and mysticism. For example, the idea of Ashwani Kumars and their miraculous power. The study was mostly confined to metallurgy and medicine, and the research was essentially based on the desire to attain the heavenly stature, which later degraded into human greed. It is related to the craving for becoming rich through conversion of any element to gold, and also to become immortal, or at least to attain disease-free long life by taking the elixir of life or amruta. Where the use of heavy toxic elements like mercury was prescribed. However, the fundamentals of chemistry involving the constituents of matter was considered to be a part of philosophy. Like Kapila had used Sankhya philosophy to describe the matras, and Kanada propounded the concepts of Anu and Parmanu through Naya Vaiseshika philosophy. In this session, we will analyze the knowledge and expertise of the chemists of ancient India. Ancient India, and also what we have lost in course of time, like the identification of Soma plant or the Soma creeper, and the techniques used in zinc metallurgy, rust-free iron, and wood steel. We will also touch upon our strength on dyes and pigments, cosmetics, perfumes, metallurgy, etc. Of course, the analysis of scientists and historians will be on different perspectives. As already mentioned by Dr. Chaudhary, IIT Kharagpur offers a course on the history of science and technology in ancient India, whose component on Rasayana has been taught by me for last several semesters. We are fortunate enough to have two illustrious speakers in this session. The first speaker is Professor B.M. Dev, the author of the magnum opus on the theme of the webinar, namely the Peacock in Splendor. He is one of the pioneers of the theoretical chemistry research in India. He is a fellow of the World Academy of Sciences, Indian National Science Academy, and Indian Academy of Sciences. So, he has received numerous awards. Just to name one is the prestigious Santiswarup Bhattacharya Prize, and incidentally, he was my PhD mentor. Our second speaker is an internationally famous inorganic chemist, Professor Samaras Bhattacharya from Jadavpur University. He is one of the most knowledgeable persons in the life and work of Acharya Prafulla Chandra Ray, the author of the book on the Hindu Rasayana. Professor Bhattacharya is a fellow of the Indian Academy of Sciences and the West Bengal Academy of Science and Technology, and has received several awards, including the coveted Santiswarup Bhattacharya Prize. Now, each speaker will speak for 25 minutes. The audience is requested to send their questions and queries to the chat box. At the end of this session, Professors Anup Ayappan and Sabyasachi Mishra will forward the questions to the speakers. Would like to request the speakers to stick to the time. May I now request Professor Dev to deliver his talk. Professor Dev, please.
Thank you, Professor Chakraj, for your kind introduction. I would also like to thank the organizing team of IIT Kharagpur for kindly inviting me to participate in this webinar. I'm going to talk on some aspects of chemical thoughts and chemical techniques in ancient and medieval India. This is a legacy of Acharya Sir Prafulla Chandra Ray and Acharya Sir Brajendranath Dev, two outstanding scholars of their time. Subsequently, of course, there have been other significant research workers. This talk is based on the book mentioned by Professor Chakraj, the chemistry chapter particularly, in the book The Peacock in Splendor, Science, Literature and Art in Ancient and Medieval India. The book contains extensive documentation and illustrations Considerable checking and rechecking of facts have been done before inclusion in the book. This is the cover of the book, and it has 10 chapters. Looking at the first chapter, any discussion on Indian culture and civilization has to go back to the Indus Valley civilization, 3300 BC to 1900 BC. And if we can identify a central theme in Indian culture and civilization, it is holism. The ancient Indian, incidentally, can everybody hear me? Hello? Can everybody hear me?
We can hear you, sir.
Yes, we can hear you.
Yeah, we can hear
Yes, sir. Yes.
Okay. So concerning holism, ancient Indians believed that everything in the universe is connected to everything else. Let us first hear what Professor Max Muller had said. In this study of the history of the human mind, in this study of ourselves, of our true selves, India occupies a place second to no other country. Whatever sphere of the human mind you may select for your special study, whether it be language or religion or mythology or philosophy, whether it be laws or customs, art or science, everywhere you have to go to India, whether you like it or not, because some of the most valuable and most instructive materials in the history of man are treasured up in India and India only. We now enter chemistry. Based on archaeological evidence, chemistry in ancient India began in the 4th millennium BC. For example, the glazed pottery found in Mohenjo-daro was the earliest such example in the world, predating this technique in Mesopotamian civilization by about 1500 years. An opaque vitreous paste used for the glaze found at Mohenjo-daro had the following chemical analysis percent: silica 88.12, aluminum oxide 3.12, ferric oxide 1.82, lime 1.26, alkalis 5.04, cupric oxide 0.46. The remainder was lost on ignition. The original atomistic philosophy seems to have emerged from India. Greek scholars used to come to India to learn Indian knowledge systems. Knowledge of practical chemistry in India during 12th to 13th century AD was more advanced than that of the same period in Europe, in that the following matters were known in India, as we know from Acharya Sisire's works. Blue vitriol and certain pyrites yield a form of copper. Color of flames as a diagnostic test for metals. Metallurgy, in particular zinc, iron and steel, I will come to this later. Shushruta and Charaka, extensive pharmacopoeia. Bhagavata, 18th century AD, the last great name in Ayurveda, describes preparations of metallic compounds involving gold, silver, copper, iron, tin, lead and mercury. Use of black mercury sulfide in 10th century AD, while Europe used it in the 17th century AD. Use of toxic compounds of arsenic, mercury and iron as medicine. This was prohibited in Europe. Indeed, the fact that toxic compounds can also have medicinal application seems to have been unknown in Europe until Paracelsus pointed this out. In Sushruta Tantra around 1000 BC, there are instructions on the preparation of caustic alkali, directing that the strong lye must be preserved in an iron vessel. The neutralization of an alkali by an acid was also described by him. Sushruta was a medical practitioner and the world's oldest plastic surgeon. Rigveda, 1500 BC, the world's oldest book of knowledge and religious text, describes a woman who had lost her leg and was given an artificial iron limb. The scientific attitude towards experiments and their reproducibility, as laid down by Dundukanatha in his book Rasendra Chintamani, Gems of Chemical Principles, 13th to 14th century AD. However, Meghnad placed him in the 9th century AD. So Dundukanatha said, I've heard much from the lips of seven. I've seen many formulae well established in scripture, but I'm not recording any which I have not done myself. I'm fearlessly recording only those that I have carried out before my elder with my own hand. Only they are to be regarded as real teachers who can show by experiment what they teach. They are the deserving pupils who can actually perform them after having learned from their teachers. This is quoted from Meghnad Shah's presidential address to the Indian Science Congress, Bombay, 1934. This may be compared with the empiricism of Roger Bacon, 1214 to 1294 AD. Incidentally, the reproducibility of result is an essential criterion in science. We now come to dyes and pigments. From 1000 BC to 1500 AD, numerous dyes and pigments of plant, animal, and mineral origin were employed. Some examples are shown here. This is indigo plant, safflower, lodra. This is lac resin. These are a few examples of modern lac bangles. This is Kermes insect on a tree, cochineal insects on cactus. This is cinnabar, mainly mercuric sulfide, the only known mineral of mercury. This is red lead, mainly Pb3O4, litharge, mainly lead oxide, chrysocolla, mainly hydrated copper silicate, malachite, mainly hydrated copper carbonate. These patterns that you see on malachite are formed over many years due to nonlinear dynamics. Lapis lazuli, which is essentially sodium, calcium, aluminum silicate, with H3 minus radical anion, the reason for the intense blue color. This is an artist's view of Rasasala, namely the chemical laboratory. Some of the apparatus employed in a Rasasala shown here, of course there were many more. We have here Koshti, Piriyak Yantram, Dola Yantram, Svedani Yantram, Adak Yantram. We now come to perfumery. A very significant name is Gangadhara, who wrote a treatise on Gandhasara. Period is uncertain. What Gandhasara did was this: classification of aromatic substances from plant and animal sources into 8 categories, processes described, and elaborate prescriptions laid down for preparing more than 200,000 perfumes in principle from elaborate matrices. We shall soon see an example. Ancient India's export of perfumes outshone even that of gold, and India did export a lot of gold. This is an 8 by 8 matrix of 64 fragrant substances with various mixing proportions so that you can prepare a huge number of perfumes out of this matrix. Most of the fragrant substances in this matrix have not been identified so far. Whatever we have identified, we are not sure whether they are the same as the ancient ones. Now come to the concept of atomism as a philosophy. This is Nea Vaisheshika, from the Indian philosophical systems, which was propounded by one other, the particle eater, in 600 BC. These years that I mentioned, they are about, not absolutely precise. 9 categories of substances, 4 materials, namely earth, water, air, and fire, and 5 non-materials, namely ether, space, time, self, and mind. Each material is made of a different kind of atom, namely anu or paramanu, which is very small, indivisible, indestructible, spherical, and suprasensible. We now know the modern concept of the atom to be spherical. The diameter of a paramanu was given a measure at least twice. The highly significant Mahayana Buddhist text, Lalita Vistara, 100 BC to 200 AD, gave the diameter of an atom as 0.675 into 10 to the power minus 8 centimeters. Note the diameter of the innermost Bohr orbit of the hydrogen atom as 1.06 into 10 to the power minus 8 centimeters. Varaha-Mihira, 505 AD to 587 AD, Varaha-Mihira's Brihat Samhita gave the value as 7.26 nanometers. It was said that a particle of this size should be visible against a slanted sunbeam. Both values are calculated by BNZ, assuming one hasta to be 18 inches. Atoms were set in motion at some primordial stage by an unseen force. This motion enables 2 atoms to form a dyad, 3 dyads form a triad, 4 triads form a quad, and so on, leading to the formation of bulk matter. Dissociation proceeds in an inverse way. Individual atoms cease to play a role after combination. 2 like atoms, as for example of earth, can enter into combination, but 2 unlike atoms, as for example earth and air, cannot. However, 2 unlike atoms, say A and B, can come in contact with each other. This contact stimulates the formation of separate dyads of both A and B, namely A2 and B2. The 2 dyads can then link up with each other. In fact, there is a justification of this from thermodynamic studies of solvent mixtures. Anyway, to proceed, thus aggregation into both homogeneous and heterogeneous bulk matter was explained. Also, the formation of new compounds among the primary elements was not precluded by this prescription. The different properties of bulk substances are due to the different structural alignments of atoms in each substance. This appears to be the earliest connection made between structure and function of atoms, molecules, and bulk matter. And this is the central theme of the modern science of materials, including atoms, molecules, and bulk matter. Mind is also atomic, but not soul. Now consider Bertrand Russell's philosophy of logical atomism, proposing atoms of thought. However, please note that this sophisticated atomistic philosophy played no part in developing basic principles of chemistry in ancient and medieval India. Question is why? That's a long drawn answer, so I would skip it here. A comparison of India's atomistic philosophy with Greek atomistic philosophy. Greek atomistic view seems to be younger, propagated by Empedocles, Lysippus, and Democritus in the 5th century BC, followed by Lucretius and Plato, 4th century BC. Greek view says atoms are individual building blocks of the physical world. They differ in shapes and sizes, but have no other qualitative difference. Atoms are in perpetual motion in an unexplained way. Fire, air, water, earth, and soul are atomic. Indian view says soul is not atomic. There was no Greek concept like diet, triads, quartz, etc. No explanation of how bulk matter formed in dissociated. In contrast to the Indian concept of spherical atoms, Plato considered the atoms of fire, air, water, and earth to be tetrahedral, octahedral, icosahedral, and cubic in shape, respectively. No Greek estimate of sizes of atoms, in contrast to the Indian estimate. Aristotle, 384 BC to 322 BC, had rejected the Greek atomistic view of the universe, which thus lasted for barely 200 years, in contrast to the Indian view, which lasted for 2,200 years. Aristotle's view was dominant in Europe until 17th century AD, when the atomistic view was resurrected in Europe by Pierre Gassendi and René Descartes of France. For nearly 200 years, it is the less sophisticated Greek atomistic view that has been and is being taught to Indian students of chemistry and physics. Shouldn't the more sophisticated and older Indian view be also taught? We now come to metallurgy, which began in India from the 4th millennium BC. While Europe mastered glass and China mastered pottery and cement, India mastered metal, as for example zinc, rust-free iron, and wood or crucible steel. These three have been called metallurgical wonders of the world. Here we'll discuss only zinc due to lack of time. Zinc 400 BC to 1800 AD. This is a glorious but tragic chapter in Indian metallurgy. The metallurgy of zinc was perfected in India by 400 BC, as for example in Zawar, Rajasthan. More than 2,000 years before it was done in the West. In the West, a process similar to the Indian one was patented. Zinc was extracted from the ore sphalerite, which is mainly zinc sulfide with dolomite, which again is mainly calcium carbonate. First, zinc oxide was made from the ore by burning it in air, and then reduced to metallic zinc by carbon. With the closure of the Zawar mines by the turn of the 18th century, the magnificent zinc metallurgy of India came to an unceremonious end. This is a sample of sphalerite. This is very important. Problems concerning zinc metallurgy, which the ancient Indians must have faced and solved. The boiling point of zinc metal is lower by about 350 Kelvin than the minimum temperature necessary for the extraction of zinc from zinc oxide. This means that zinc metal can only be extracted in the vapor form, requiring both condensation and distillation. An appropriate reducing environment is essential for zinc extraction. Otherwise, the zinc vapor gets rapidly oxidized to form philosopher's wool, that is, back to zinc oxide. The reaction zinc oxide plus carbon giving zinc plus carbon monoxide has an enthalpy change, delta H equal to plus 57 kilocalories per mole. This is highly endothermic, so heat has to be supplied. The estimated minimum temperature necessary for extracting zinc from zinc oxide in a retort made of a refractory material is 1523 Kelvin. There is thus a serious challenge of maintaining proper temperature all through the extraction and collection process. This is a section of a zinc furnace obtained from Zawar, Rajasthan. It has a 6x6 array of 36 resorts within a refractory framework. These are the retorts. This is one section, 6 retorts, and this is a condensing vessel. So there are 36 condensing vessels. From this webinar, we have come to know that India has always been the land of vision, of the eye. In conclusion, may I beg your indulgence to speak a few years. Indian culture and civilization is a vast ocean. So far, we have gathered only a few drops of Indian knowledge system which is gifted to the world. Please note that there are about 10,000 Sanskrit manuscripts in existence, and no doubt, and nearly equal number of manuscripts and ancient Tamil, which has its own magnificent grammar and geometry. And for magnificent grammar and literature, geometry is also part of that. Therefore, there is an urgent need. In fact, the need is never greater, perhaps, than today. An urgent need for a meticulous, scholarly, and holistic exploration of India's past, assisted by a battery of powerful scientific methods and unencumbered by any bias towards meaningless glorification and senseless vilification. Thank you very much for your kind attention.
Okay. Let's thank Professor Dept for his highly informative presentation. And we will just now invite Professor Samaras Bhattacharya for his presentation. Professor Samaras Bhattacharya, please.
Yes. 1 second. Let me. Am I there on the screen?
Not yet, not yet. Yeah, now it's coming, now it's coming. Yes, it has come.
Professor Chattaraj?
Yes, we can see your screen now.
Okay.
Yeah, we can see your screen. Please go ahead.
Thank you. Okay, so let me begin by thanking Professor Rotin Chattaraj for, bringing me here as a speaker in this very well organized webinar on Bharata-Tirtha. And today I have planned to talk about Acharya Prafulla Chandra Rai, whom we all regard as the pioneer of chemical research in our country. And I'll begin by showing a photograph of Acharya B.C. Rai and a quotation made by none other than Mahatma Gandhi about Acharya Rai. He said, "It is difficult to believe that the man in simple Indian dress, wearing simpler manner, could possibly be the greatest scientist and professor." Truly, he was a saint-like person in his dress and attitude, but deep inside he was a very serious scientist, a very serious chemical researcher. He was born 2nd August 1861 and died on June 16th, 1944. So that essentially means he was alive on this planet for roughly 83 years. I love to share quotations and photographs, but I'll show only a few of them today because of time limitation, not a problem. One is made by P.C. Rai himself, about himself, that I became a chemist almost by mistake. Because at the very early age, he was not very fond of chemistry as a subject, but later on he got attracted to the subject chemistry. I'll explain why in a minute. And the other remark was made by Acharya Jagadish Chandra Bose, another Acharya, who was senior to P.C. Ray by around 3 years. And he said that P.C. Ray has been a pathfinder and originator. So truly he was a pathfinder and originator as far as chemical research and chemical industry in India are concerned. A brief, sort of biodata of P.C. Ray. He was born on, as I already said, I have already said, August 2, 1861, in a village which is now in Bangladesh. Village name is Raruli in the district of Jessore. Subsequently in Khulna, which is in Bangladesh. His father was Harish Chandra Rai, a son of a local zamindar. He was a man of taste, learning and liberal views. This is important to understand the views and attitude of P.C. Ray himself. His mother, Bhuvan Mohini Devi, was also an accomplished lady of enlightened views. And I like to request the audience to just keep in mind the time. Okay, it's 1861 to 1944. On the average, more than 100 years back. Acharya P.C. Ray was indeed a very renowned professor of chemistry, no doubt, and he was also a great scientist of his time. But in addition to that, he was a true patriot, okay, and a social worker. There is no time for me today to talk about all these attributes of P.C. Ray. And he was, I have already told, pioneer of chemical research and chemical industry in India. The very first chemical industry that was established in our country was Bengal Chemical and Pharmaceutical Works. That was established by P.C. Ray in 1902. And he also used to love literature, library and biography, and he knew half a dozen languages. So if you, sincerely consider all this together, one, needs to be astonished by how a single person can, have all these attributes. Okay, let me briefly talk about his early education. He did his FA, first arts course, that was there at that time, and chemistry was a compulsory subject. P.C. Ray was a student of the then Metropolitan College, which is now Vidyasagar College in Calcutta, but he used to attend the chemistry lectures by Alexander Bedler in Presidency College. And he said himself, I began almost unconsciously to be attracted to this branch of science. Here I'll take a pause and say a few words that, I already commented in the very beginning that P.C. Ray was not particularly attracted to chemistry as a subject in the very beginning during his school days, later school days. But it was Alexander Bedler, his teacher at Presidency College, who kind of attracted him to this branch of science. Okay, so, teachers indeed have a very significant influence on the students. I have seen students leaving chemistry and joining other disciplines because of, bad teaching, and I have seen the reverse as well in my own life. So I feel that it is, it all depends on the teacher, of course, how he or she can attract the young minds to a particular discipline. In 1882, he won the Gilchrist Scholarship and went to Edinburgh University. 1885, he got his BSc degree from there, and in 1887, he obtained his DSc degree, and his subject of research was double sulfates. This subject may sound a bit, dilute today, but today it is 2020, and he did his research in earlier during 1885 to 1887, and his PhD supervisor was Alexander Graham Brown. And if you take a note of this fact that he had two Alexanders, one as his chemistry teacher, Alexander Pedler in Presidency College, and the second Alexander was his PhD supervisor at Edinburgh University, and both of them had great influence on PC in his future career and activities. And I am very fond of showing pictures. I already said this is Alexander Pedler on the left side of this slide, and Alexander Graham Brown on the right side, his PhD supervisor. And this is another picture of PC Ray. And I find the similarity between all three of them is that other than, they are all chemistry lovers, but other than that, they all have beards of different types. Okay, that is another thing I like to attract your attention. Research career, 1887, he did his DSc already, I said it. He came back to India in 1888, and almost for 1 full year he didn't have any formal job anywhere. In 1889, he joined the Presidency College, Department of Chemistry, and he was there till 1916. In 1916, please take a note that he was 55 in 1916. He left Presidency College at the call of Sir Ashutosh Mukherjee, the then Vice Chancellor of Calcutta University, and joined the chemistry department at the Science College of Calcutta University in 1916. And he was there till 1944, okay, till his death in Science College itself. He used to live in a small room in the Science College at the Rajabazar campus itself. He had a different and a separate house also, but he used to stay in the Science College itself because he would spend most of his time to research and teaching. That was the sole purpose of staying within the Science College campus itself. Some of his famous students are J.C. Bose, Inarthar, J.N. Mukherjee, B.B. Dey, and many more. This is a slide I love to share with all of you. Let me read the text first. It was in 1886 that postgraduate teaching in chemistry was introduced for the first time in India. So MSc in chemistry was initiated or started in 1886 in India. A new chemical laboratory was set up in 1893, 7 years later, at the Presidency College, Calcutta, and was properly equipped with imported instruments. Okay, and we are now in 2020, and even today, if we need to equip our labs, we need to import instruments from abroad. Okay, we don't have, instruments or even an NMR tube, manufactured in our own country. Here in the rooms of Presidency College, we saw the dawn of pure chemical research. So this was extracted from an article published in a journal not known to many. It's the Indian Journal of History of Science, and this article was published in 1989. The author is Aparajita Boshu from Bangabashi College, Calcutta. Okay, so and please remember that P.C. Ray joined Presidency College in 1889. So P.C. Ray was instrumental in initiating chemical research at Presidency College since the very beginning. Categories of research contributions of Acharya P.C. Ray. P.C. Ray is mostly known for his famous, contribution with regard to synthesis and characterization of mercurous nitride, but he did other things as well. Okay, so here I have categorized the research contribution of Acharya B.C. Ray, metal nitrites with special reference to mercurous nitrite, of course, ammonium nitrite and related compounds, organic sulfur compounds. Many did not know that he did a significant amount of research work on organic synthesis, and of course coordination compounds, which is precisely my own research area. Publications he published. Publication number is a very parameter, is a very useful parameter. We assess people in terms of their publication, which is not always very correct, and the number is always relative. 158 is less than many other numbers and more larger than many other numbers, but at that time 158 publications means a lot. Even today it means a lot to me, at least. So he published around 52 articles on metal nitrites and hyponitrites, and 19 on ammonium nitrate and related compounds, organic sulfur compounds 38, fluoroorganic compounds, which many people did not know about, that he did research on fluoroorganic compounds, coordination compounds 14, and others 30. Okay. So it's not only mercurous nitrite, but of course discovery of mercurous nitrite was phenomenal. He himself said in his biography that the discovery of mercurous nitrite opened a new chapter in my life. Now, what is so important about mercurous nitrite? Mercury has two, actually it's not two, at least three, 0, 1 and +2 oxidation states. But mercury 1 is unstable towards disproportionation to mercury 2 and elemental mercury, which is of course mercury in 0 oxidation state. And the other component of this compound, namely the anion, is a nitrite anion, which is also unstable and can undergo fissile decomposition. So mercurous nitrite is truly an example of a stable compound composed of two relatively unstable ions. Philosophically thinking also, it is really wonderful that one stable compound can be generated out of two unstable components. It is relevant to mention here that stable mercury 1 complexes are scarce in literature even today. And he, he synthesized or discovered the mercurous nitrite accidentally. The target was to prepare water-soluble mercurous nitrate as an intermediate for synthesis of calomel, mercurous chloride. So the reaction was carried out with elemental mercury in excess and nitric acid dilute, and it resulted into formation of a yellow crystalline solid, which on analysis turned out to be mercurous nitrite. The formula, as we express it, Ag2NO2 twice. Now I must add at this point that there has been a local star in the newspaper about 10-15 years ago, that mercurous nitrite cannot be synthesized. It's a false claim by Acharya B.C. Ray, and someone even went ahead and made a statement that he did some thermodynamic calculations and concluded that this cannot be synthesized. So the claim made by B.C. Ray was a false claim. So that mentally affected many people around our country, and some of them took the trouble of sort of resynthesize it and succeeded in it. But before I tell that, show that story, show that research, let me quickly tell the people who are present that nitrite ion may bind to a metal center in 3 different ways: through the lone pair on nitrogen, or through the lone pairs on the 2 oxygens, or as a monodentate ligand through one of the 2 oxygens. So these are 3 possibilities in principle as far as mode of binding is concerned. Now this is the final result, that these 3 people, Subhash Samanta, Sriprata Goswami and Animesh Chakraborty, at the Indian Association for the Cultivation of Science, they tried to synthesize this mercurous nitrite by following the exact method, and I like to underline the word exact method as described by P.C. Ray in his publication, and they could do it reproducibly as many times as they wished. And what you see here is a crystal structure of the Hg2NO2 unit. Okay, and crystal structure is regarded and must be regarded as a photo identification of every chemical species. Okay, so if you throw in a crystal structure, that means the characterization is undeniable. And when they did it and tried and published it in Indian Journal of Chemistry, in Indian Journal of Chemistry in 2011, they came to know that two other groups, one in 1985 and the other in 1986, they also solved the crystal structure of the same complex, same chemical species earlier. So there is definite proof that it would be prepared, synthesized without any problem, only if you follow the exact method as described by P.C. Ray in his publication. Okay, and this is the arrangement of the units within the crystal. Let me skip this. P.C. Ray did also a significant amount of work on chemistry of hyponitrite. I'll just highlight one slide. Hyponitrites at that time were prepared by interaction of metal nitrite, which are water soluble, with sodium hyponitrite, and thereby they used to prepare metal hyponitrite. And this particular slide I'm very fond of, because P.C. Ray synthesized and separated mercurous and mercuric hyponitrite through this method. Okay, and let me quickly explain this as much as I can. He started with a mixture of water-soluble nitrites of both mercurous mercury and mercuric mercury, and he added dilute aqueous solution of sodium hyponitrite, which resulted in the formation of both mercurous hyponitrite as well as mercuric hyponitrite. And mercurous hyponitrite is not very soluble. This is only partly or sparingly soluble, as we call it, so it got precipitated mostly. So it could be filtered out, and whatever remaining amount of mercurous was there could be separated by addition of little bit of sodium chloride solution, because mercurous chloride is highly insoluble. So the residual mercurous mercury could be separated in the form of mercurous chloride, and then upon addition of again excess of sodium hyponitrite, he could synthesize and isolate the mercuric hyponitrite. So this apparently simple method, I said apparently because at that time there was no established method of preparing and separating things. Okay, so but he was able to synthesize, prepare both these hyponitrites as well as separate them plainly. And these days there are other and simpler methods available, but if you think respect that time, you need to respect this chemistry as well. This is another slide. I'll quickly talk about it. Preparation and purification of ammonium nitrite. At the first glance, it may look very simple to everybody that ammonium nitrite for preparation, what is the big deal? But I don't see any students or any research scholars in the participants list. But I hope some of them are there watching through YouTube. But if you ask them to prepare ammonium nitrite in the lab tomorrow, they will be in trouble, because you need to have two sources, one for the ammonium ion and the other for the nitrite ion. And it's not very simple to prepare ammonium nitrite that way. But what P.C. Ray could come up with at his time is really remarkable. He interacted ammonium chloride and silver nitrite. Silver has a very strong affinity towards chloride. So this simple mixing these two things together resulted in the formation of silver chloride, which is insoluble, so that precipitates out, leaving behind quantitative amount of ammonium nitrite in solution. And that could be easily crystallized out by evaporation of the solution. A very simple and easy method, and let me tell you, even today, to extract chloride from any metal complexes, people use silver ion, because silver has a very, very strong affinity for chloride. So this simple method may look really simple today, but it is still used as a very effective method. And he purified ammonium nitride by through sublimation. Ammonium nitride is regarded as something which is explosive. Okay. And it's not really advisable to heat up ammonium nitride because it's known to explode under thermal condition. But he could do it successfully and repeatedly without any problem under reduced pressure. And ammonium nitride was not observed to decompose even at 60 degrees centigrade. So if you think about all these apparently simple reactions, keeping the time in mind, you'll be astonished that how serious a researcher he was, because what I am stating today is not the outcome of only one single experiment. He did it repeatedly, and now I am speaking as if it is a very simple observation, but it was not really. Lot of failures were there behind these successful reactions. Okay, I'll skip this slide because I can see I don't have much time left. He utilized the same methodology to prepare other, alkyl ammonium nitrides as well. So I'll skip this slide and I'll touch upon his research work on organic sulfur compounds. Okay, this is one a reaction that I like to show the audience, that he was successful in preparing this polymeric compound, if you allow me to call it a polymeric compound, with a molecular weight as high as 3068. And this is the first instance. And please take a note of the word first. So this was the first instance of a crystalline organic sulfur compound of such high molecular weight as 3068. And the reaction is apparently simple. Any reaction, after it is done, successfully for the first time and it's written on a piece of paper, it looks very simple. So this is not an exception to that. Simple reaction, dibromoethane, 1,2-dibromoethane reacted with the disodium salt of 1,2-dithiol of ethane. Okay, so disodium salt of ethylene dithiol and dibromoethane reaction, and these are the products, the polymeric product and sodium bromide. So the polymeric product settles out of the solution, no difficulty at all. But once I showed this slide to one of a very well-known polymer chemist, and he was very astonished to find that a PC dye at his time could synthesize polymeric species of this much high molecular weight as 3068. This is another very interesting reaction, as I already mentioned, that reactions when it's all done looks very simple, that this is camphor, normal camphor, and he could substitute the oxygen with sulfur. On a piece of paper, it looks always simple, but if I ask you to carry out a similar reaction that convert acetone to thioacetone, you'll be in trouble. But PC dye did it successfully back in 1934 and published this chemistry in Nature magazine. Okay, the reaction conditions are really pretty simple. So, whenever I look at these slides or show these slides, I get amazed to feel the imagination and the dedication that he had. That worked behind all these reactions. Okay? This is another reactions for making cyclic organic organothio compounds. I will not go into any details because I can see my time is almost over. This is another reaction, one shot. In one shot, he could convert this sulfur containing compound into the corresponding sulfur. Sulfur can be oxidized in two stages, first to sulfoxide and then to sulfur. And these molecules are biologically or pharmaceutically very important. Sulfone compounds, they have potential application in pharmacy. Such methods of oxidizing sulfur, controlled oxidation in some cases to sulfoxide and sulfone are very well respected from industrial point of view, and he could come up with an apparently simple method by oxidizing with potassium permanganate in the presence of dilute sulfuric acid. Very interesting reaction. Even this is practiced by organic chemists even today. He also did work on chemosensors. This is one quick example whereby he used this chloropicrine as a reagent to sort of chemically sense thiol compounds. Okay, this is the reaction. I will not try to elaborate. So this is the initial product, okay, which then react within themselves and release N2O3, and which is a thermally unstable species compound. It decomposes into NO and NO2. NO2 has a very specific brown color. NO also, which time converts into NO2, and so through the generation of brown colored gas, one can recognize the presence of organic organosulfur compounds in any sample. So during his time, P.C. Ray also, synthesized or came up with these chemosensors. Okay, these days you will see so many publications on chemosensors, but 100 years back, on the average, he did work on chemosensors as well. He also worked on coordination compounds. I'll just show one example, then I'll just stop. The nature of work was he synthesized complexes of different type and characterized them with regard to composition and stereochemistry, and separated them also. This is very interesting. I'll show one quick example that he synthesized iridium complex with this is the thioether, okay, sulfur analog of the common ether, and that was his ligand. He reacted with iridium compound, ammonium chloroiridate. This is the reaction condition, and at the end he isolated and separated two different isomers of the same species with regard to empirical formula. Okay, IRCl3 and 3 of these ligands. Okay, one isomer was orange in color and the other isomer was red in color, and they were separated based on their different solubility. One is more soluble in non-polar solvent like benzene, the other was more, less soluble in benzene but more soluble in chloroform, and the solubility difference is a manifestation of the difference in stereochemistry. The trans type of complex compounds are less polar, and so they are more soluble in non-polar solvents, and the cis type of isomers, they are polar in character, and they are less soluble in non-polar and more soluble in polar solvents. So that was the basis, and this was a tedious method. If you think about it in 2020, one would be astonished to realize how many times he needed to do it, this fractional, sort of separation in a separating funnel using these two solvents. So the orange isomer goes preferably in benzene, the red isomer goes preferably in chloroform. And he assigned structures to both the isomers, but after crystal structure determination, the orange isomer was found to be meridional in nature, and the red isomer was found to be a mixture of these two. One is a complex cation and one is complex anion. But if you average it, the empirical formula was exact. And please try to understand that even finding out the composition was so difficult at that time. No sophisticated instruments were available at that time. So I think as my time is up, I'll stop here. Chairman Sir, Professor Chattaraj, I solicit or I seek your comment with regard to time. I believe my time is over. Is that so?
No, a couple of minutes you can.
Okay, because I like to show one last slide. That is I'll skip all this.
Yes.
Okay. He prepared so many other complexes. If you look at all this, I'm very emotional about all these works done at that time. That means on the average about 100 years back. So cisplatin, everybody knows, is a drug today practiced to treat some types of cancers. Okay, if you visit, if you go to any cancer clinic, you will find this cisplatin is administered to patients with a certain kind of tumors. But this is a cisplatin kind of analog which he could prepare during his time through this method, substitution method. This is one platinum complex. He substituted the thioligands, okay, with ethylene diamine and prepared this kind of complex, characterized them unambiguously, and determined their melting point, which is regarded as a very, very important parameter to for each individual compound. Okay, so I really feel very, very amazed to look at all these reactions that he carried out back at that time and successfully characterized them. I'll skip majority of the, in spite of being a very productive scientist, he could find time to write all this history of Hindu chemistry, 2 volumes, big ones. If anybody is interested, they can go through this book. He found this Bengal chemical and pharmaceutical work industry, the first of its kind in our country in 1902. He was the founder president of Indian Chemical Society, 1924, and he got many recognitions, but I'll highlight only the last one. In 2012, the Royal Society of Chemistry honored him, his life and work, with the first ever chemical landmark plaque outside Europe. Okay. So this is something I am very fond of sharing, and this is a picture that at Presidency College, this group of people gathered together, and there was a big event for this plaque giving ceremony. And some references, okay, where from I extracted all these informations. I also wrote an article along with Professor Shri in the Resonance magazine in 2001, I believe. And this last reference is also, I find it very useful. If somebody is interested to look into his life and work, then this is a publication by Indian Chemical Society one can go through. And this is the last slide I like to share. It's a quotation made by P.C. Ray himself in 1932. He was 71 years old at that time. While a student at Edinburgh, I found to my regret that every civilized country, including Japan, was adding to the world's stock of knowledge, but that unhappy India was lagging behind. I dreamt a dream that, God willing, a time would come when she too would contribute her quota. Half a century has since rolled by. My dream I have now the gratification of finding fairly materialized. Fairly. A new era has evidently dawned upon India. Our sons have taken the zealous pursuit of different branches of science. May the torch thus kindled burn with greater brilliance from generation to generation. This was his hope in 1932, and we don't know how much of his expectation we could fulfill so far. So with this note, I like to close and thank you all for your patient hearing. Thank you very much.
Okay, let's thank Professor Samaras Bhattacharya for the excellent presentation. And now I pass it on to Professors Anup and Sabasati Mishra.
So should I close this presentation?
Yeah, you can close the presentation now. If there is any question from the audience, so the reporters will just forward forward those questions to you and Professor Dept.
Okay.
there are many comments, but questions. There's one question in YouTube, Sage,
Okay.
that is asking for books
Okay.
to learn about the ancient science, ancient chemistry, literature.
Okay. So maybe Professor Dev will be able to answer that. Professor Dev.
Professor Dev.
Unmute, please, sir.
Sir, you have to.
So people are willing to know references to learn about in ancient history of chemistry. I believe that's the comment. Huh?
That's the comment. So, books on
Professor Arpan, you read it out once again, please. He probably missed. Professor Chattaraj, I don't know. Somebody should.
Yeah, the question that sorry. The question is being asked, is there any reference book that you would like to suggest from where one can learn about ancient Indian science? Professor Dev?
Yes, I can, if you excuse me, I can only suggest the book that I wrote over many years, and it has an exhaustive list of references up to December 2013, just before the publication of the book. For chemistry, there is a list of for every chapter there is a list of references. So I would suggest one might look at those.
And I can add, if you permit, to go through the 2 volumes of History of Hindu Chemistry by P.C. Ray himself.
Yes.
Okay.
And both the speakers had there in their slides, they had references to several books. I'm sure people can have access to that. Yes. While we are waiting for additional questions in YouTube or in other forum, I have got one question for Professor Dev. When you mentioned that the size of the atom was estimated with such great accuracy, it was quite puzzling. And also the idea that the atoms were spherical in shape. Can you comment on what kind of thought process went behind it? Was there any what was the driving principle that led them to believe that atoms were spherical in nature, and also the dimension that you mentioned, what led them to those numbers?
Yeah, actually, in many instances, in studies in ancient India, we sometimes do not find the method. In Lalita Vistara, for example, there was a length scale given by Prince Siddhartha when he was being examined by the foremost mathematician in his father's court. And so he gave a length scale which would, if you convert it, then it would come to this number that I mentioned. In Bhattacharyya treatise, there was another length scale, which again, if you convert it, because in both length scales, hosto appears. So taking hosto to be 18 inches, which may not be correct because our hosto may not be their hosto. But whatever, taking this as 18 inches, we come to those numbers. But for example, you will see again and again, people who have pursued Indian sciences have again and again said that how did the ancient Indians come up with so accurate values? We don't have any answer. We do not know the methodology at all. So there it is as if in their manuscript, they have simply given the result without the methodology, unless we come across other manuscripts, which will perhaps someday show the methodology. Everywhere, astronomy, mathematics, everywhere, they have always, one historian from abroad said, it is astonishing that every time the Indians shot their arrows accurately. So that method is not known.
Thank you, Professor. There has been another question. There has always been a quest to convert base metal into gold. Was alchemy ever successful?
I don't think so. You see, the main reason, as far as I could see, alchemy is not considered science at all. But as far as I could see, gold, ancient Indians considered gold to be heavenly. Warriors in the ancient times used to put on golden ornaments as well as certain bodily decorations before they would go into battle. So gold was always considered heavenly, and then therefore the alchemical attempts in India to prepare gold by some kind of transmutation is like ascending heaven. So they tried to prepare gold, they tried to prepare nectar. Both motivation was to be heavenly, to ascend into the realm of the gods. Naturally, it was not successful. How can it? There is no science there. If you recall, if I may take an example, some years ago, a person named Ramar Pillai became quite a darling of the media, Indian media, because he claimed to be preparing petrol from certain leaves and branches. And DST organized his demonstration in IIT Delhi. IIT Delhi faculty members were naturally skeptical, and they felt that nothing has been established. It was later turned out to be a hoax and perhaps a fraud. But right from independence, this claim to prepare gold like this was demonstrated in presence of Jawaharlal Nehru. He just debunked it. He said nothing has been seen. So one should not bother about it.
There is another question. What was the Indian measure of temperature?
That is difficult. I don't know that. Maybe somebody can enlighten. I've tried to find it out. You see, Pratin Chakraj was asking the question, how did they measure temperature? How could they control temperature in zinc? Because you have to know the temperature. So I don't know. I don't know that.
Question, can I ask? I'm Professor Ram Subramaniam.
Yes, please.
Professor Dev, I was curious to know what was the basis on which you take hasta to be 18 inches. Normally, hasta is specified to be 24 angulas.
Yeah. Okay. Actually, there are different measures for angula. So in these two length scales, in Lalita Vistara and Varahamihira text, there is a ratio between angula and hasta. So I did not go to angula at all. I took hasta. Because, angula, the width of the middle finger would vary from person to person. So I took hasta, not angula. And hasta, if you take the the Indian later conversion, two cubits make a yard. and that is a hostel. So that is it. Somebody can take another measure and come up with another diameter of the atom, as long as you specify what you are doing. Okay?
So is there any more question? Any more question?
Yes. Can you hear me?
Yes.
Hello.
Yes, we can hear you.
Yeah. So actually, in my history course, when I am talking about the small numbers, I mean, there is a culture of large numbers and then there is a culture of small numbers. So I do this, what Professor Dev has mentioned, and it is to the scale of 7. So this 10 to the power 7 Parmanu Rajas that they have used. So the Prince Bodhisattva, he answered that thing. So it is very interesting to
Yes, please. Okay. This perhaps you are referring to Lalita Vistara, where this term Paramanu Raja has been employed. Yeah. So this is the length scale. I'm not going into the detail of this length scale, because then it goes to Dhanush, to Yajana, etc. So I just took Hasta, because Dhanush, for example, had been employed in the length of the daily iron pillar, but that is another matter. So there are various length scales given by different people. I took only these two because I was curious about the concept of the atom. And did they come across, or did they suggest some quantitative measure of the diameters? Okay.
So I'm quite happy that you made this estimate and took it as 18 inches, and it is actually close to 18 inches even if one were to measure one's own hasta. So on average, if you just take the height of the person to be 5.5 feet, maybe the hasta will turn out to be 18 inches. So one can just make a thumb rule. But my question was it based on this kind of a thumb rule, or is it something which is based on certain other things? That is what I wanted to know.
It is not based on any rule. Assuming that hasta, because I have to convert this to a present day value and can compare it with other numbers. So present day hasta would be regarded as 18 inches. Okay, 2 hastas would be a yard, right? So that is why, yard would be 36 inches. So hasta I took as 18 inches. But there is nothing sacrosanct about it. Only thing is try to take something which does not vary from person to person. But in the olden days, a person generally would not be 5.5 feet unless he is a dwarf. So these people would be quite tall. For example, Alexander's army were quite astounded to see King Puru. And the Greek historians had said Puru's height was something like present day 9.5 feet or something. So I don't know. But no need to take all this very seriously. I think you need to be objective and just don't believe anything blindly.
As a matter of fact, in Bengali, Puru is the width, not the height. Protein, let us not talk about Rabindranath Tagore's sarcastic poem about Bengalis.
মাথায় ছোট বহরে বড়.
So, is there any say other question? No.
I don't see any other questions in either WebEx or YouTube or Facebook. So I think it's
Okay.
time to close the session.
So,
over to Professor Chatraj.
yeah, if there is no other question, let's thank both the speakers and both the reporters and also the organizers. And I am just handing over the charge to Professor Joyce.
Thank you, Professor Chattaraj. I think today has been a brilliant day, and the entire day ended with another brilliant session. As per Professor Dept, there is no alchemy, and alchemy has never been successful, and alchemy is not a science, and base metals have never been converted to gold. But we ordinary people here, under the banner of Bharata-Tirtha, by these brilliant lectures, we have been raised from base level to a gold level. So I think that is where we transform, which is just not a chemical transformation, it is actually the level of the mind, going from the Iron Age to the Golden Mind Age, which is symbolic. And that's what India has always stood for, not to take things at a literally level, but at a metaphorical level. So I think that has happened by listening to the two brilliant speakers, Professor Dept. Sir, we have gone through your book, and it's a brilliant book. I have a copy of your book, The Peacock in Splendor. The Peacock in Splendor, it's a brilliant book. And the lecture by Professor Bhattacharya was heart-filling, as if we are seeing Professor P.C. Ray standing here in Netaji Auditorium and blessing us, and he's trying to say that pick up the gauntlet of science, of Indian sciences, and march for a brilliant future. Don't take things lightly. Lead a simple life. Believe in a life of plain living and extremely high thinking. Please believe in a life of plain living and extremely high thinking. I think if we believe in Professor Acharya Prafulla Chandra Roy, that is what we should believe in, because technical knowledge is always number two. What is number one is man-making, the right human being. Only a right human being can take up the responsibility of good and humane science. So Professor Ray was both, and in that sense he was a complete scientist, philosopher, and a transformer of the society. And it came out so well in these two presentations by our, it's Professor Dept. I mean, he's almost like our guru, by virtue of his book and by virtue of his prodigy. And the very heart-filling presentation by Professor Bhattacharya, which was just not a presentation, I think it was a tribute. It was a pranam. It was a pranam at the lotus feet of Acharya, at the lotus feet of Acharya. So I think that is something which we have realized in Bharata-Tirtha, which Ramji, Professor Ramasubramaniam from IIT Bombay was just saying in the preceding session, because it is a tirtha, it is the water that makes all the change. So chemistry is a science of flows and waters and chemicals and reactions and transmutations and transformations. So I think this is the lesson that we have learned from the two esteemed speakers, Professor Dept and Professor Bhattacharya, and it was very efficiently coordinated by Professor Chattaraj and also by the two very deft reporters, Dr. Mishra and Dr. Ayappan. So our heartfelt thanks also goes to them. So with this, we come to a successful session of the second day of Bharata-Tirtha, as coined by Gurudev Rabindranath Thakur. And tomorrow we have the third and the last day, and we have about 5 sessions. So we'll begin tomorrow at 10 o'clock, where we concentrate on Ayurveda, the biological and the physiological sciences of the human body. And so we request all the speakers, all the listeners, and all the participants to switch into the YouTube channel close to 9:50 or 55 and be ready. and the speakers will be obviously on the WebEx link. Thank you so much, sir, and it was really an honor to have all of you with us. And the thanks goes to all of you on behalf of the mother of IIT systems, which is IIT Kharagpur.
Excuse me. This is Dept speaking. Can you hear me?
Yes, sir.
Yes.
Yes. I have a small plea. You see, we frequently spell Acharya Professor Chandra Rai's surname as Ray or Roy. Professor Chandra never liked it. He always spelled his name as Rai, with the accent emphasis on A. So I believe, out of respect for Professor Rai, we should stick to that. Thank you.
Thank you, sir.
So, Professor Joy.
Yes, Professor Kumar.